And we've kind of already found the first part of the interval of convergence, but when you are finding the interval of convergence, each endpoint must be separately tested for convergence or divergence. Okay. All right, so the first thing that we always have to do for either radius or interval of convergence is use the ratio test. And this is actually the result of the ratio test right here, but I want to work one more with the ratio test because I want to make sure that you are good to go on using the ratio test. So we always start with limit as n approaches infinity. Absolute value, a sub n plus 1 will be x to the n plus 1 over n plus 1, and then times the reciprocal of a sub n. All right, so x to the n plus 1 over x to the n simplifies to x on top. I still have an n on top and an n plus 1 on the bottom. So the limit as n approaches infinity, I need to concentrate on the degree of n on top and bottom. Right, the degrees of n are the same, so therefore the limit is the ratio of leading coefficients. Well, what's the ratio of leading coefficients? X, right, because in this problem x is just considered a coefficient because we're taking the limit as n approaches infinity. So that limit is the absolute value of x. All right, so the very first thing that I always do is I take that limit, which was the absolute value of x, and I want to find the values of x that will make the series converge. So therefore, I have to set it less than 1, because in order to converge using the ratio test, that limit needs to be less than 1, which means that negative 1 is less than x is less than 1. Now, if this had been what is the radius of convergence, what would the answer be? 1, right. Your center is at x equals 0, because that's the middle of negative 1 and 1. Also, if you look at your power series up here, you know that it's centered at 0. So I can go 1 in either direction and still converge. All right, so the radius of convergence is 1, just to review the last ones. This question's not really asking that. All right, so now we're going to test the endpoints of our interval of convergence. So my first endpoint is x equal negative 1. And all that means to do is consider this series when x equals negative 1. So if I plug in a negative 1 for x, then this series is the sum from n equals 1 to infinity of negative 1 to the n over n. And I need to determine whether this series converges or diverges. And this is where this entire chapter comes together. What type of series is that? It's an alternating. Very good. That's half the battle, is just determining what type of series it is and therefore what test. So since it's alternating, let's use the alternating series test. There are two things I have to prove. One of them is that a sub n plus 1 needs to be less than or equal to a sub n. My terms need to be decreasing. And remember that a sub n does not include the negative 1 to the power. So a sub n is really just 1 over n. So a sub n plus 1 is 1 over n plus 1. Less than or equal to 1 over n? Yes. And then the other half of the alternating series test is the limit as n approaches infinity of a sub n. And what does this limit equal? 0, which is what it needs to equal. So therefore, this one converges by the alternating series test. This is actually a special alternating series because it's an alternating. It is a p-series. It's a special p-series. Harmonic. It is an alternating harmonic series. The alternating harmonic will always converge, and you're welcome to use that as your justification from here on out. So next time you see negative 1 to the n power over n, you can say, that's the alternating harmonic. It converges. I'm moving on. All right, your other endpoint is x equals 1. So when we plug x equal 1 into the series, we get 1 to the n, which is just 1, over n. So does that converge or diverge? It diverges because it's the harmonic, the regular harmonic. So therefore, the actual interval of convergence includes negative 1, but does not include positive 1. So the ratio test kind of gives you this rudimentary interval of convergence, but you have to go back and test the endpoints. And the good news about testing the endpoints is that usually it's going to create a pretty simple and easy series to determine whether it converges or diverges. All right, find the interval of convergence for this next problem. We always start with the ratio test. If you do the ratio test, you end up with that limit equaling absolute value of x plus 1 over 2. To save time, I'm just telling you that when you do the ratio test, you get absolute value of x plus 1 over 2. On your homework, you'll have to do the ratio test. So, in order to figure out which x values make this series converge, the absolute value of x plus 1 over 2 must be less than 1. Or x plus 1 over 2 needs to be between negative 1 and positive 1. So how can I get x by itself in the middle? Okay, multiply by 2 and subtract 1. Okay, let's check to make sure we've done this right. What's the center of the power series? Negative 1, because of the x plus 1 to the n. So the center of the power series is negative 1. Is negative 1 smack dab in the middle of negative 3 and 1? Yes. What's the radius of convergence? 2. Good. All right. So my interval is between negative 3 and 1, but I have to check to make sure see if I have to include negative 3 and 1. So when x equals negative 3, my series is negative 1 to the n. Negative 3 plus 1 is negative 2 to the n over 2 to the n. Somebody please simplify that for me. 1 to the n? Yeah. Because every single term is to the n power, I can think of that as negative 1 times negative 2 divided by 2, all to the n power. All right, 1 to the n power. Converge or diverge? Why? Okay. If you think about just figuring out some of the terms of this, when n is 1, you have 1 to the 1. When n is 2, you have 1 squared, which is still 1. When n is 3, you have 1 cubed, which is still 1. So 1 plus 1 plus 1 plus 1 plus 1 forever and ever and ever definitely diverges. In that sense, we're diverging by the nth term test, because the limit as n approaches infinity of a sub n equals 1, does not equal 0. 1 to the n is also another type of series that you're familiar with. It's geometric, right? And your r is 1. And in order for a geometric series to converge, r has to be less than 1. So 2 different ways to think about that. All right, so that one diverges. The other endpoint is x equals 1. So when x equals 1, our series is negative 1 to the n times 2 to the n over 2 to the n, which just simplifies to negative 1 to the n. So does negative 1 to the n converge or diverge? It also diverges. 2 ways to think about it, in my opinion. If you think about it being geometric, r is negative 1, and the absolute value of r has to be less than 1. The nth term test, the limit as n approaches infinity of a sub n, is fluctuating between 1 and negative 1, does not equal 0. So either way, it diverges. Or it's an alternating series, and the limit as n approaches infinity of 1 does not equal 0. So neither endpoint is included on this one, so the interval of convergence is just negative 3 to 1. So what that really means is that any number between negative 3 and 1, but not including negative 3 or 1, when you plug it up in here to x, that series will converge. All right, so if this little parenthesis wasn't here, and I just said find the interval of convergence, what's the first thing you would do? Ratio test. Okay, but I've done the ratio test for you and told you that that limit is the absolute value of x. So to find the values of x that will make the series converge, I need for that limit of the absolute value of x to be less than 1. So x is between negative 1 and 1. And therefore, what is the radius of convergence? 1, again, good. Okay, so now I just need to test my endpoints. So if x is -1, then my series is n equals 1 to infinity, -1 to the n over n squared. It is a p-series, and it's also alternating. So since it's alternating, let's think in terms of the nth term, the alternating series test. A sub n plus 1 would be 1 over n plus 1 squared, and a sub n is 1 over n squared. So that's true. And the limit as n approaches infinity of 1 over n squared does equal 0. So it converges. Every alternating p-series converges, no matter what p is. So from here on out, all alternating p-series converge. You may use that as a reason. So if you see -1 to the n over n squared, it's an alternating p-series, it converges. -1 to the n over n to the 1/2, alternating p-series still converges. So even if p is less than 1, an alternating p-series still converges. 1 over the square root of n does not converge, but -1 to the n over square root of n does converge because it's alternating. Okay, and then if x equals +1, my series is 1 over n squared, which that's just a regular p-series. So I do have to look at the value of p. It converges because p is greater than 1. So I converge at both endpoints. Therefore, every x value between -1 and +1, including those endpoints, would make that series converge and therefore have a finite sum. So radius of convergence and interval of convergence, start with the ratio test, set that limit less than 1, and go from there.